Hello, my name is Shunhua Jiang, and today I'm going to talk about our paper, NearOptimal TimeEnergy Trade-offs for Deterministic Leader Election. This is joint work with Yi-Jun, Chang, and Duan. Okay. So first, let me introduce the model that we consider. We consider single-hop radio networks. A radio network is a distributed system of devices that are equipped with radio receivers. So in this paper, we consider single-hop radio networks where all devices can communicate via a single communication channel. We use capital N to denote the number of possible IDs, and we use lowercase n to denote the number of devices. In this illustration, we show an example of a single-hop radio network where the ID space is 10, and there are 5 devices present in this instance. We assume that time is divided into discrete slots, and communication proceeds in synchronous rounds. In each round, each device has 3 possible actions. It can either transmit or listen or stays idle. A message is successfully transmitted when exactly one device transmits, and we measure the energy of a device as the number of time slots that this energy is not idle. So both transmit and listen will cost 1 unit of energy. And the energy complexity of an algorithm is measured as the maximum energy over all devices. The motivation to define this energy complexity is that in radio networks, often energy is the scarcest resource for devices. The model also needs to specify the ability of the devices to detect collision. A collision happens when more than one device is transmitting a message. There are 4 models for collision detection. The strongest model is called strong CD. In this model, a device have both sender side and receiver side collision detection. When more than 2 devices transmit, all transmitters and all listeners will receive a collision signal. The second model is called sender CD. In this model, only the transmitters can distinguish between collision and silence, and the listeners cannot distinguish whether more than one devices are transmitting or there is no device that is transmitting. And the third model is called receiver CD. In this model, only the listeners can have the ability to detect collisions, and the sender cannot distinguish whether he is the only transmitter or there are other transmitters. And finally, there is the model of no CD. So in this model, transmitters receive no feedback, and the listeners either receive the message or it always hears silence. Okay. In this paper, we consider the fundamental problem of leader election, and we focus on deterministic algorithms for this problem. The goal of leader election is to have exactly one device identifies itself as the leader, and all the other devices identify themselves as non-leaders. So a leader election algorithm will succeed if there exists a time slot where the leader speaks and all the non-leaders listens, and then they reach this consensus of a leader. This is a well-studied problem in the literature. Recently, a paper in 2019 by Jiang et al. Proved a tight bound for the energy complexity of leader election in all 4 models. They show that when the model allows sender-side collision detection, the energy complexity is log n, where the capital N is the size of the ID space. And when the model doesn't allow sender-side collision detection, then the energy complexity is log n. However, in the algorithms presented in this paper, their time complexity is not optimal. For example, in the strong CD model, when their algorithm reaches log n energy, their time complexity is of order n. And there exists another trade-off when the energy complexity and the time complexity are both log n. Their algorithm can be generalized to obtain a time-energy trade-off, where when the energy complexity is k, the time complexity is k plus capital N divided by 2 to the k. Note that this trade-off matches these two algorithms. And in the no-CD model, it has long been known that a time complexity of order n and an energy complexity of order log n are both tight. So the question becomes, what is the tight time-energy trade-off in other models? Is this trade-off given by this paper by Chang et al. In 2019 tight? The lower bound of log n and log n by Jiang et al. Only works when there are only two devices. When there are more devices, the problem could potentially become much easier. In this paper by Jiang et al., they also provide a result that shows when the number of devices is of the same order as the size of the ID space, the problem can be solved super efficiently in alpha n time, where alpha is the inverse Ackermann function. In this paper, we ask the question, what is the best algorithm for these dense instances? So next, let me present an overview of our result. So the first part of our result is about nearly tight time-energy trade-offs. We provide algorithms that improve upon this time-space trade-off algorithm of the previous paper. We show that in both the strong CD model and the standard CD model, there exists an algorithm with energy complexity k and time complexity k times capital N to the 1 over k plus little n to the 1 plus epsilon, where epsilon is an arbitrarily small constant. We also provide a lower bound that nearly matches this upper bound. So in the strong CD model, we prove that when the energy is k, the time has to be larger than k times capital N to the 1 over k. And this lower bound is proved for two devices. It is already known in the literature that when in the standard CD model, when the energy is k, time has to be at least order of little n. So this shows that up to this epsilon constant, this algorithm is tight. The second part of our result is about a faster algorithm for leader election in all models for the dense instances. And we also provide matching lower bounds. We show that in the strong CD model and the standard CD model, there exists an algorithm with energy complexity log of capital N over small n. And in the receiver CD model and the no CD model, there exists an algorithm with energy complexity log capital N divided by small n. And both of these algorithms are tight. And note that when small n has the same order as capital N, both of these two algorithms will achieve constant energy for leader election. So this improves upon the previous paper. Okay, next I will go into the technical details of our results. First, let me talk about the first part of our result, which is the near optimal time-energy trade-off. Let me first introduce our algorithm. So it suffices to show this algorithm in the standard CD model because the strong CD model is a stronger model. So in this slide, I will show an algorithm in the standard CD model where the energy complexity is k and the time complexity is k times n to the 1 over k. This algorithm holds when the number of devices is bounded by n to the 1 over k to 1 minus some constant. And in order to make this algorithm work for arbitrary number of devices, we will lose this small n to the 1 plus epsilon factor in the final running time. Our algorithm uses the following notion of a good partition. We say a partition of the ID space is good for a set of devices if there exists a group in the partition that contains exactly one device. For example, In this illustration, we showed an example where the ID space is 15, and there are 3 devices, 6, 5, 6, and 12. So this partition is a good partition for this set of devices because there exists this group that contains only 1 devices. We prove a lemma that says that there exist k partitions of the ID space into n to the 1 over k groups, such that for any set of devices, there exists at least 1 partition that is good for this set. This lemma is proved by probabilistic method. So we prove that the probability that random k partitions satisfy this property is non-zero. So there must exist such k partitions. Then the algorithm will make use of these k partitions. The algorithm works as follows. It enumerates over the k partitions, and for each partition, it enumerates over all of its groups, and it lets all devices of each group transmit a message at the same time, and the algorithm will recurse to all the devices that hear no collision. So here is an example. So when considering this partition, all the devices in the first group speaks first, and all the devices in the second group speaks first. They will hear collision, so we will not recurse down to this group. And then all the devices in the third group will speak at the same time. And since there is only 1 device in this group, it doesn't hear collision. Since there are n to the 1 over k groups, there are at most n to the 1 over k devices that hear no collision, and there must exist at least 1 such device by this lemma statement. The total energy of this algorithm is k, because each device will speak once when we enumerate over each partition, and the total time complexity of this algorithm is k times n to the 1 over k. Because we enumerate over k partitions, and in each partition we enumerate over n to the 1 over k groups. This finishes the proof of our algorithm. Next, I will briefly talk about how we prove the matching lower bound. So we prove that an algorithm that works for 2 devices, when it has energy k, its time complexity has to be at least k times n to the 1 over k. So the proof works as follows. First, we observe that the algorithm for each ID will correspond to a tree. Here is an example of a protocol tree. In each time slot, a device has 3 possible actions. It could either transmit a message, or listens for messages, or stays idle. When the device either transmits or listens, we need to specify what is its next action if it receives collision or silence feedback from the communication channel. This protocol tree has a height t, where t is the time complexity, and on each pass of the tree, there will be k number of transmit and listen actions. For each ID, we can define a pass AI on the tree, such that if the action is transmit, then we go to the collision branch, and if the action is listen, then we go to the silence branch. The key observation is that if the 2 devices have the same pass in their protocol tree, then the algorithm cannot possibly succeed, because the 2 devices will always transmit and listen at the same time, and they will receive collision signal when they transmit and receive silence signal when they listen, so they will both follow the same path. This means the number of different paths need to be smaller than the ID space, so that the algorithm can assign a different path for each different ID. And the total number of different paths is t choose k times 2 to the k, and this is bounded by t to the k's power divided by k to the k. So this equation will give us the time complexity is at least k times n to the 1 over k. This finishes the proof of our lower bound result. Next, I will present the second part of our result, which is algorithms and lower bounds for dense instances. Let me first present our algorithms. I will first show a simple algorithm that will have energy complexity n divided by n, and then I will show how to improve this to log n over n in the surround city model and the center city model, and improve this to the log of n over n in the receiver city and no city model. Okay. The idea of this algorithm is that the algorithm will maintain an ordered list S, and each device in S is responsible to recruit n over n IDs. After that, it drops out of S. After the end of the algorithm, the set S will be non-empty, and each device in the set S will know its order in the set, so they can find a leader in this set S. Okay, here is an illustration for this algorithm. So in the beginning, we will have an empty set, and the algorithm will have n rounds. In the first time slot, we'll consider the first ID. So these IDs are all empty. There's no device with these IDs. So the algorithm will just pause in this time slot. In the fifth time slot, this device will speak, and it will find out that the set S is empty. So it will put itself in the set S. And now this device 5 will be responsible to recruit all the devices in this group. So it will speak to this device 6, and then it knows that, okay, 6 is present. So it will put 6, we will put 6 into the list S, and then we'll move on. So after recruiting all the devices in this group, the device 5 will drop out from the list S, and then the next device 6 will be responsible to recruit all the devices in the next group of IDs. And in the end of the algorithm, we will get a ordered list S that is non-empty. The total energy complexity of this algorithm is capital N divided by small n, and the total time complexity of this algorithm is capital N. Okay, next we show how to improve this to log n over n and log n over n. So for each group of this n over n IDs, instead of let a device speaks to each of them, we will use the census algorithm of this previous paper to agree on an ordering within this group. Then a device in the ordered list only needs to communicate with one device in the group. And the census algorithm have complexity log n prime in the surround city model and the center city model, where n prime is the size of the ID space, and it has complexity log n prime in the receiver city model and no city model. So for our case, n prime would equal to capital N divided by small n, because we're restricting to this group of that many of IDs. So this will give us the final result. We will get this log n over n energy complexity for these two models and log n over n energy complexity for these two models. I will talk about the lower bound for these dense incidences. So let me first prove this lower bound of log n over n for receiver CD. So recall that the algorithm for each ID would correspond to a tree, and now because we're in the receiver CD model, so when the device transmits, it cannot receive the collision signal because it cannot distinguish between collision or no collision. And we define a path similar as before. So in this path, whenever the device listens, it will always hear silence. Next, we consider a random sequence B that also have a length t, and each time slot of this B is randomly transmit or listen, each with half probability. So we say that this random sequence B matches our path AI if whenever AI transmits or listens, it's the same in B. Since the path AI will have E number of transmit and listen actions, so in expectation, the random sequence B will match with N divided by 2 to the E number of paths. Now the key observation is that the algorithm cannot succeed on the set of IDs whose path AI all matches with the same random sequence B, because these devices will always transmit at the same time and listen at the same time, so there cannot be any successful transmission of a message. So this means the number of devices is at least capital N divided by 2 to the E. And that gives us the desired lower bound of the energy complexity of log N over N. And I will briefly sketch our proof for the strong CD model. So in the strong CD model, when the device transmits a message, it will receive two feedbacks, silence or collision. So instead of considering a pass AI, now we will considering a tree where each pass will have E number of transmits and listens. And now for a tree, this 2 to the E factor will become 2 to the 2 to the E. And then we will prove that the energy complexity is at least log N over N. Okay, so basically that's it.